Alright, now we will do the finite element approximation. So this is where the coding begins once we have established everything else. So we will have 4 linear elements. A and B will be going from 1 to 3 according to our problem statement over here. Thus, we will create a linear, we will create n linear elements here. So we'll start with our coordinates. They will be linearly spaced from A to B, and we will have n plus 1 elements. We can run this here. We can see that we have indeed 1, 2, 3, 4, 5 nodes going from 1 to 3 linearly spaced. Alright, then we need to have our nodal connection, and in for linear elements, this matrix will look something like this. We have the first coordinate connecting to the second coordinate, the second connecting to the third to the fourth, and so on. That's how we establish that. And we will need to have our number of nodes, which is just going to be the total number of the total length of this vector here, which is 5 in this case. Then we can add semicolons here to suppress this output. And the first thing we will do with this mesh here is to visualize it. So for that, we will just copy in some code here. You can rewrite this. And now you can view that. So we can actually take the output of this and just copy it in here and then get rid of this if we want to, but I'm not gonna bother copying it anyways. I'm just gonna leave it as it is. But now this is what you will look at when you're applying your boundary conditions. The numbering here is important. It's telling you where your boundary conditions are going. So the solution vector u is going to exist in these nodes, and g, the natural boundary conditions, will exist on either the first or the second one, or the last one I mean. And in this case it's actually this one here, so the udx of 3. So at coordinate 3, that's node 5, we will apply boundary condition, and the essential boundary condition will be in node 1, u of 1 here. This is the first node at x is equal to 1 that has the value of 3. So u1 is known and the rest are unknown. This is what the problem is, to find out the rest of these. Yeah, and the exact solution for this problem, we can solve that using the symbolic toolbox. So we have the u of 3 is equal to -2, u of 1 is equal to 3, and we will call the variable ue for u exact, and we will plot this from 1 to 3 here using the color red. So if we do this, we will get this thing here. So we can actually, instead of creating a new figure, we will actually utilize the old one, and then we will get an overlap between these two. Just let me remove the x's here so that I can get the function like this. So this is what I have then. This is the exact solution, and this is my mesh. And somewhere here I hope to get, so the first one is given, u1 here. This is 3, so the first node is actually already established. We just need to find out the rest of these. Okay, moving on. So now we need to establish our basis functions, and these you can always copy paste from another file which I have prepared. So we can go to your folder and you can open your basis functions .mlx file here. So you have in one dimension linear basis functions and their derivatives. We have for quadratic elements and for 2D triangles and for 2D quads. We have linear, quadratic, bilinear, biquadratic. And it can get quite complicated once we get into the quadratic types here. And these of course are all defined in the Xi eta space going from 0 to 1. So now we just copy this, close this down and paste in the basis functions. And we make a notation here that this basis function used are these taken from basis function .mlx, copied. All right, now these basis functions are going to be function handles. They are defined as that. So that means that they are not symbolic, they are numeric function handles. We can evaluate them using phi of 0, for instance, like this. And if you evaluate this, this will evaluate to 1 and 0. Now I will do a section break here in order to evaluate this stuff faster and get rid of this. So once we have this, we will need to have our numerical integration set up. So that's Gauss integration. And if we take a look at our function here, we see, if you scroll down to the isoparametric mapping, we see that, okay, we have our functions here. So this will be a constant, right? Because we can see here that the derivative of phi is constant. So a constant times a constant is still a constant, so that's okay. Hold on, here. Constant times a constant is a constant, that's still okay. And here we have a linear function multiplying, and we don't have a mass matrix. So we just have these two here. So that means that the highest order of our polynomial is going to be 1. That means we can utilize first order Gauss. So I will just copy again. We will utilize the Gauss points and weights for numerical integration, the Gauss function here. So the order is going to be 1, and this actually tells us if we what the space is. So we're going from Xi equal to 0 to 1 in this case. So the midpoint is going to be 0.5 and the weight is going to be 1. And this is okay for our problem. But for every problem we need to change this depending on the highest polynomial order. So far so good. Now the system matrices and vectors. So we have our number of equations here, which is the number of nodes. So we have 1 degree of freedom per node. So that's our number of equation. And then we will pre-allocate our stiffness matrix. You can see here that I will run some of this. So the stiffness matrix in this previous run case looked like this, populated, but we will start with just zeros. So it will be 0 everywhere, and we will have 9 or 5 of them. So we can run this, you can see clearly here how they're going to look like. This is what we will get. And then we are going to assemble the element stiffnesses into these once we get running here. So now we will start looping for IL is equal to 1 to n. And the first thing we need to establish is our local nodes. So I node is going to be equal to nodes IEL. So if you run this, you can get everything will be run n times, which is 4 in this case. So the first element is between node 1 and 2, the second between 2 and 3, 3 and 4 and 5 and 4 and 5. So then we need the coordinates for these elements. So xc is equal to x node of I node. So x node is of course this vector here, and I node is going to grab these elements, 4 and 5 in this case, the last case. So if we run this, we can see here these are our coordinates, and we can verify them. Okay, 1 and 1.5, that's okay. And then 1.5 and 2, 1.5 and 2, and so on. That checks out. Now, our local coordinates. So we will have x1 for every element. That's the coordinate that is leftmost. That's going to be xc1, the first component. And then we have x2, and that's the last component. In linear elements we only have 2, but for quadratic we will have 3 nodes. So we will keep this general. So xc end. So this is our end node, the last node in this component here. So that means the last is this one, the second one. We could have written 2 here as well, but we want to keep this general. So if we change up the basis functions to a basis function that is quadratic, we will have 3 components. Our mesh will be completely different. We will have 3 components in here, and this will still work. So we want to keep this general. So now we can define our element size, h, which is in one dimension the same as the Jacobian. So this is just going to be x2 minus x1. x2 minus x1. Like so. And we can see that the element size, because of our linearly spaced nodes here, is the same, 0.5. Like so. And then we will pre-allocate our stiffness matrix. Like so, and also our load vector, which we have here now. Alright, if you take a look at our problem that we are solving, and yes, it appears that I have made an error in here. The exact solution is actually the problem statement is this is equal to 1, but I have written is equal to x over here, so I will just change that quickly and rerun this. So this is the actual problem that we are having. We will begin with a simple problem and we'll add complexity to this in future videos. So for now we just solve this basically. So we will need to have our now we have a choice here. We can of course do this just by setting this order to 1 and then integrating this without, because we know that this is just going to be 1 point integration, and we just have 1 point here. But the thing is, if we create this code in order to be changeable easily, then this will save us a lot of trouble later when we don't need to mess around with changing values in here. So we will create a for loop in here where we're looping over the Gauss points. So that's ig Gauss point I 1 to length of gp. So in our case, gp is just 1 point, so this is just going to be run once. But later, if we change order to have a higher degree order here, we will have 2 points or 3 points, and this will still function properly. So now our c is gpig, so we'll just grab the current xc for this, and the current weight iv is gv of ig, like so. And of course, if we run this, we will see here that we have the same Gauss point every time. Good. Now get rid of this, and now we can insert our stiffness matrix in here. So we will have the phi of XC. You can run this, and you can see here that the phi is, yeah, so we have to modify this. So this is not a function handle, so we will just insert a function handle here, XC, like so, and then we can run this as I've written here. And of course I'm doing this again to keep things general. If I change the order, then by changing, for instance, the if I either change the order or if I change the basis function, I want this code to work without needing to change it down here. So the phi of XC is of course constant, so we will just transpose this and multiply it by itself, and we'll get a matrix as we expected. Now we will multiply this by 1 over h, and k of course is kept 1, so multiply this by 1 over h, and multiply this again by the element 1 in this case, because this is the element length for the parametric element, which is always going to be 1. So we will multiply this by IW, the weight, and this is our stiffness matrix. Now of course k is just kept as 1. We could insert k here and set it to 1, and that would make this even more general. In fact, let's do this. So let's go up here and set k equal to 1, and then multiply by k, and here k multiplying. Now we will save this into our SE. So we do SE is equal to SE plus this, because if we have a higher order Gauss integration, then of course we will add up the function evaluation, multiplying by the weights will add up into the total integral for this numerical integration. Now this will always now integrate to a proper value as long as we set the order properly up here. So that's SE. So you can run this. You can see that, okay, k is missing. We didn't run this code up here, so we'll run this fast. And now k is set. We can run this, and we have our values in here. So far so good. Now the load vector. So for the load vector, the same thing holds. Fe is equal to Fe plus whatever the load is. So we will set this here. F is equal to 1 in this case. If we scroll up to our problem, you can see that F is equal to F is set to 1. Here, 1. So that's F, of course, here, and can do F times our phi, which is phi of C, and then we will transpose this, transposed, and multiply this by h, the element length, and multiply it by IW. And F is not set, so we will need to run this in order to set F, and then we can run this, and we'll get FE down here. Okay, so this is all we need. These two element matrices is all we need for our problem. Of course, we could also run the mass matrix in order to have this code complete and just set the this here to 0, not have it, but we'll say that for a future video. Okay, so once we have this, we will just assemble the stuff. So we have, start with F. So we have capital F here of I node, is equal to f of I node plus fe, and s of I node comma I node is equal to s of I node comma I node plus se. And if we had a mass matrix, we will do this for the mass matrix as well. But for our problem, we don't need it, so we'll just leave it as it is and then build upon this code at a later point. Okay, time to apply boundary conditions. So, but before we apply boundary conditions, we can just write out S and F here and run this, and you can see that our S matrix, stiffness matrix, has been populated and F has been populated. Alright, now we need to apply boundary conditions. So it's always good to have the mesh sketch lying around here so we can see the nodes, the numbering of the nodes and the elements, and our boundary conditions. So I will just go up and grab them and copy them in. So again, we see that the first node here at x is equal to 1, the solution is known. So that's the prescribed solution. So we will start with this. So we will say that, okay, the prescribed node, the node number that is prescribed is 1, and that the solution field U is 0, zeros, bunch of zeros, and the number of equations, and 1. So we can run this and we see here that we have a bunch of zeros. Good. Now we prescribe this. So we say U in this node is going to be this value, which is 3. And we see here that we have our value 3. Good. Now we need to find out all the other nodes. Right. So we have the prescribed node, which is 1, and we need to get the free nodes, which are all except the first one, so 2, 3, 4, and 5. So in order to achieve this, in order to get the free nodes, we will take the difference between all nodes and the prescribed nodes. That will give us the free nodes. So for that, and we use the function setDiff. And if you run this, we can see we have 2, 3, 4, and 5. Perfect. Now we need to handle the boundary conditions, the natural boundary conditions, which is this one here. So for that end, we will create a vector called G, which is going to be zeros, number of equations, and 1. So a bunch of zeros here, and we will take a look at what is happening. So our system basically looks like this. So we have, in this case here, I assume we have 9 nodes. Never mind that. Just think that we have 9 nodes currently. In fact, let me change this to 8, and then we'll have the same picture. So n is equal to 8, and run this, and run this. And we have, probably need to copy my picture here. In here. So 9 nodes. Okay, so so we have the stiffness matrix, which is 9 by 9, and we have our U vector here, where the first one, node 1, is known. This is 3. Then we have our load vector here, and we will have our G matrix added to this. So this will look like something like this. And yeah, in fact, okay, I need to modify this. So G0, G1, and G9. So G9, the last one here, is going to be -2, and the first one and everything in between is just going to be insert column, no, row, is just going to be zeros. so like this. So that's our G vector. The reason, okay, in general, what we have is the following. So the G vector basically looks like this. We have negative du dx of a va, and then we have a bunch of zeros, and then at the very end we have du dx b of vb. The reason this is negative here is because of the expansion of this here. If we expand this, we can see here that we have db minus du dx of a. So the upper limit minus the lower limit. So the lower limit is always going to be negative. That's why there is a negative sign in here. Okay, so far so good. So that's G, right? And then G end is -2 here. So you can add this to this. So you can say G end, the last node, is going to be -2. Now we have applied the boundary condition. Perfect. Run this and we can see that, all right, there's a -2 there. So now we need to modify the right hand side, because u is known, or in either case, even if it's not known, we will always modify the right hand side. That means the following. We will take whatever is known here, u1, and we will move that number, that column, to the right hand side. So that means this column here, the first one, will be moved and multiplied by u1 on this side here. And the next step will be to eliminate the first row and the first column. So you can see here that we start at the second column and then the second row, and then u1 is eliminated, and we have f2 and then so on. And we can add a g to this. In fact, we can actually call the whole right hand side, we can call it fr. That's our f. It's a modified right hand side, and it's our g thing here. So in code we can say that in general we have the following situation, and we can get rid of this thing here. We can actually move G down here, so point that out. So G1 is minus, and then whatever value we have, in this case it's 0, so we just keep it 0. And G, the last one, is whatever value we have. So that's where we apply boundary conditions. So apply natural boundary conditions. So if we had the boundary conditions where this here would be known at the first node, then that value would be negative, and then whatever value we would have would be in here inside the parentheses. Alright, now modifying the right hand side. So we have fr equal to our capital F, and then we can add g to this first, so it plus g, and then minus, we take s, and we take all of the, let's see here, s, we take all rows, and then the prescribed columns, which is going to be the first one, and we multiply this by u prescribed. And this works even if u was several values were prescribed. This would also work in that case. So if you run this, you can see that now the FR looks completely different than before, because the solution in U actually modifies the load vector. All right, and the last step is just solving the linear system. So U of free is going to be equal to S of free, and then linear solve backslash operator, fr, free. We run this, we get our solution. So we see here that we have gotten, the first one is of course whatever we had here, and then the last one is 1, and we can check this here, like, okay, this goes down to 1, that looks good, and then stuff in between. So we will plot this now, so we can see that we have something that looks proper. And because we already have a figure here, I will just go up and change this. So type hold on and get rid of this. Actually, yeah, I have the same code in there, so no. Create a new figure, plot the original and plot the new one. Run this, and there we go. I have 8 nodes, and we have our solution going perfectly through the points. So how about that? Okay, so now in order to, obviously we see that we have something that is good because we have the exact solution, but we will also see in the next video how to do the L2 error.